So talking about some Unit 1 stuff, and it really ties into everything, kind of thinking about polar covalent bonds, right? Identifying polar covalent bonds. Alright. Alright, so the gist of organic chemistry at the end of the day is you gotta be able to decide which bonds are more reactive than others, right? And think about which bonds are more polar, right? That one element in the bond is more likely to have the electrons, right? Helps us understand where those bonds are most likely to break, right? A polar bond is more likely to break. It's more reactive. It's less, it's a less strong bond. But the other way we can think about this too is, right, to understand how boiling points work, melting points work, and things like that too, right? So instead of talking about, when we talk about polar covalent bonds, let's say we have something like this, a couple of molecules. Right, so you have three molecules like this, like three different functional groups, right? So how does polar covalent bonds relate to functional groups? So all these molecules have polar bonds, right? They all have polar CO bonds, for the very least, right? You all see the polar CO bonds, right? But they also, there's another component to polarity, right? That's not just like within, right? One of the things you got to remember when you think about molecules, a lot of times we'll draw just one of each, but right, in a bottle, right? If I have like a glass bottle of phenol here, right? The molecules themselves are interacting with each other, right? There's intermolecular forces, right, between this molecule and another molecule of itself, right? Notice how those are the intermolecular forces, the ones we think about for boiling points and melting points, right? So if you have really strong, right, really strong intermolecular forces, your boiling point is going to be high or low? High, right? And the way to think about that, right, think about water, right? Is it easy to boil water? It's not, actually, right? Water boils at 100 degrees Celsius. So let's throw water in the mix here, right? Water boils at 100 degrees. Which one of these molecules is like water? The first one, right? We identify the same kind of OH, right? So what these guys can do is do hydrogen bonding with themselves, right? So essentially what that means is, and we know now, right? Calling something a hydrogen bond, it's a misnomer, right? Hydrogen bonding is actually not a bond, right? It's an intermolecular interaction, right? It's not a bond. You call it a hydrogen bond, but it's actually not a bond, right? It's an interaction. But if you can hydrogen bond with yourself, you're gonna have really strong intermolecular forces, right? It's the best intermolecular force we got. So if you look for polar bonds to hydrogen, and also areas of electron density, right? So water has oxygen with electron lone pairs, and then a polar OH bond, right? So there's intermolecular forces there. This alcohol can do hydrogen bonding with itself, right? So these will have high boiling points. So if I rank, this one would have the highest boiling point, and melting point too, if it's a solid or whatever. But now what about these two? So now I put these two on here because I want you to think more about what we learned in this last unit, right? One of these molecules is different than the other. What's different? What kind of functional group does this molecule have? This one is a ether, and this one is a? Good. Now, one of these can do something the other one can't. They both can do resonance, but this ester can do a particular type of resonance just with the ester portion, right? These electrons can come down, and these could go up. And so that would create a resonance structure right? Like that. Now that resonance structure, right, is not like saying that, it's not to say that, right, this ester exists like this, but some of the time it's like this, right? So which one of these molecules is going to have stronger intermolecular forces, right? The ester here, or the ether, do you think? The ester, right? Probably because of this resonance structure, right? Because this resonance structure now has a minus end and a plus end. So if this found another ester, right, they could do some intermolecular forces. Not hydrogen bonding, but they could do some like electrostatic or London dispersion kind of forces, right? Versus this one. So that kind of ties back at least some of the resonance stuff we know now, right? We've talked about polarity and TLC and things like that, right? At least you could you could rationalize why if it's different. Now, I can't look at these and tell you this is going to boil at this temperature and these for sure will always be different, right? It's like anything you do, you'd get the numbers and you'd say, okay, I can rationalize it after the fact, right? Chemists get the data and then we make sense of it later. Very rarely are we good at predicting things. It's always after the fact. So I would say this is 2, and then this would be 3. Oh yeah, sure. Okay, let's draw a chair structure. What should we put on our chair structure? Bromine. What else should we put on our chair structure? Chlorine. What else should we put in there? Anything else? One more thing? OH. Okay. Let's do this. We'll do this a couple ways. We'll do a ring flip, and then we'll also draw it flat with wedges and hatches. So the first thing you should do is what? Number your carbons. And I'm just arbitrarily choosing, right? This is completely arbitrary. 1, 2, 3, 4, 5, 6. So obviously there's other things on carbon 2 and 4. And what are those other things in 6? I say draw them in. Hydrogens, right? And we know, right? So we'll do the ring flip first. So for the ring flip, I'm gonna essentially take, right, if you look at the chair, and this is the head of the chair, and this is the feet rest. What I'm gonna do is I'm gonna take the head and pull it down. I'm gonna take the feet and pull it up. That's the ring flip. All right. So now where's carbon 1 at? Carbon 1 is right here, right? That's carbon 1. This is 2, 3, 4, 5, and 6. Good. Did any bonds break? No bonds broke. No bonds broke, right? Good. So bromine is still on carbon 1, right? Now bromine was equatorial. What's it going to be after the ring flip? It's going to be axial, right? So ring flip, whatever was axial becomes equatorial. Whatever was equatorial becomes axial. Now the place on the ring, the wedge and the hatch has nothing to do with axial and equatorial. Nothing to do with it. You can be axial down and axial up. It doesn't matter. You could be either way. But now if I look at this, the way I have it drawn, this bromine is pointing up or down? Down. So when I do a ring flip, where does it have to be pointing? It has to be down. Has to be down. Has to be down. So it's gonna. We already know it's gonna be axial, right? So here on carbon 1, axial is down. Carbon 3, the OH is also pointing which direction? Down. So now the OH was equatorial before. Now it's gonna be axial. Let's see, chlorine was on carbon 5. Was the chlorine up or down? Up, and what position was it? Axial, so now it's going to be up and equatorial. Good. I know it's hard. The hardest part for this stuff usually is where to start. So I usually go to the top corners or the bottom. In the top corner, I always draw one straight up. That's axial up. That means the also have equatorial down. Then the next one's axial down, equatorial up. It's back and forth. Right? So if you can do one, you can go back through and do all the other ones. Switch it every time, yep. Okay, so I can ask another question here. Which one of these two conformations is more stable? Do you think it's going to be A or B? Which going to be the more stable conformation? Why A? They have more space, sterics, right? We don't want things to be axial, right? Also, you could have looked and said, well, bromine's even bigger than chlorine, right? If it was just bromine and chlorine, you can look at the periodic table and say chlorine is smaller than bromine. So if we had to put somebody axial, let's put the smaller thing axial, right? Because when you're axial, notice, right? 1, 2, 3, they call these 1, 3 diaxial interactions, right? So it's sterics argument. Things basically elements bumping into each other. They don't want to be next to each other. So A is the most stable conformation. Now, let's draw a 6-member ring that represents this. So now be careful. I can draw the same 6-member ring to represent both of these conformations, right? Because this is flat. Cherry structures are in 3 dimensions. So what didn't change from here to here? If the bromine was down, was the bromine down in B? Has to be, right? All you're changing is axial and equatorial. So on a ring, right, I could have drawn B first just as easily as I could have drawn A first. Right? So let's number of carbons in our ring. 1, 2, 3, 4, 5, 6. So carbon 1 has a bromine. I'm just going to draw it hatched. Carbon 3 has an OH. Is it wedged or hatched, carbon 3, the OH? Should be hatched. Carbon 5 has a chlorine. Should that be wedged or hatched? That one wedged. And you could have also drawn, right, the enantiomer of this too. Everything opposite would have been fine too. Right? I'm arbitrarily picking this top part to be wedged. It's completely arbitrary. So do a Fisher projection. All right. So Fisher projection, it's implied, although it's not drawn, that this is coming out at you. The horizontal pieces are coming out at you, and the vertical pieces are going away from you. All right. So we've got to figure out, is this R or S? So the next thing we need to do is rank these pieces, right? Red, white, and blue, right? Red being 1, blue being 2, or white being 2, blue being 3, right? So let's rank these. So which one has the highest rank? So, yeah, which one has the highest rank? Anybody know? One on top. Right at the bat, you should be able to see that. Right, you go here, carbon, 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 carbon. You see right away this guy's bonded to 3 carbons. Everyone else has an H. So you should just automatically say, hopefully, number 1. Right, what would number 2 be? It will be, well, actually, let's do an easier one. What's the lowest rank? You usually go highest to lowest. The lowest would be the bottom one. So that'd be 4. And now we're stuck with the double bond one. Right? So carbon, carbon, carbon to 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 H, carbon to H. Go one out. This carbon is actually bonded, right, to a carbon. And this one is bonded to 3 hydrogens, right? So this gets priority. The double bond. 3. So now you got to take your model out and match it to one of these 2. We've decided it is S. So if we compare an ester to a nitrogen, or an amide here, right? The question, what's different? The part that's different, right? They're both carbonyls. The only part that's different is the oxygen and the nitrogen part. So what's different about oxygen and nitrogen? How are they different from each other? Electronegativity, right? Size, you can tell a little bit, but which one's more electronegative, oxygen or nitrogen? So which one do you think is going to hold this lone pairs tighter? Probably the oxygen, right? So oxygen, remember, we talked about this with IR. Remember, esters have their frequencies at a higher, they have their higher wave number frequency, right? Because this bond is so polar. Remember, it's a tighter frequency stretch. That's why esters are at 1745, right? Because this is more important, the oxygen pulling away electron density, versus with amides, right? They can actually do resonance, and because of this resonance, life exists, right? This is right. This strength of this bond, because it does resonance, this carbon-nitrogen bond has some double bond character, and what we'll learn about next semester is, right, carbonyls aren't all the same reactivity, right? Some are more reactive than others, right? And thankfully, because of this resonance, right, this is like a double bond, at least part of the time, and that makes it really strong, right? And because of that, amides don't react, right? And also because of that, right, they don't boil or melt very well because they have really, really good dipoles, and so they actually have really strong intermolecular forces, right? And so back to the IR part, right, about 1695 or maybe even lower for amides, right? Because just like this has double bond character, the CO bond, CO double bond now, has some single bond character. Yeah, so right, it's all back to electronegativity, right? And resonance for this. Let's do a alpha cleavage of an alcohol. We'll do two. We'll do both an alpha and we'll do a heterolytic and a homolytic cleavage. Right? So we put a molecule in the mass spec, and hopefully I'm gonna try to come up with some cool experiments so we can do some mass spec next semester. Some electron beam. What's the first thing that's gonna get knocked out? An electron. Which electron? Lone pair, let's say, right? That gets ejected, right? Boom, gone. Fish hook, right? Single-headed arrow. I'm gonna draw this twice because we're gonna demonstrate two different ways. So there's one way, the same, because we're going to show both the heterolytic and the homolytic cleavage here. I think it is helpful to number carbons, why not? 1, 2, 3, 4, 5, 2, 3, 4, 5. So which one do you want to do first? The heterolytic or homolytic? Hetero. That one's easier, right? Hetero, Rio. That's just nonsense. Rio.
No, that doesn't sound. The other one doesn't sound.
Hetero.
Hetero. There you go. Yep.
Lytic.
Heterolytic. Yeah.
There it is. Good job. Learning experience. So heterolytic cleavage, removing how many electrons? Heterolytic means hetero means two. Which bond am I going to break here?
Carbon.
Which carbon?
Carbon.
Carbon 3, right? The idea being here, right? Oxygen has a plus charge. Does oxygen want to have a plus charge? Well, no. That bond breaks. Number my carbons. 1, 2, 3, 4, 5. Notice how many electrons are on the oxygen? Right, it had 2, and it had the 1, and then it got 2 more, right? So it's 1, 2, 3, 4, 5. But then it also has 1 in that bond, right? How many valence electrons does oxygen have? 6. So does it have all of its valence electrons here? It does have all its valence electrons. It doesn't have a full octet, but it does have all its valence electrons. So what else do I need to do? What did I forget? Got to balance my charge. Plus charge on where? And which piece do you actually see in the mass spec? Only the positive charge thing, right? That's the only part you see in the mass spec. Good.
This is going to sound really dumb, but wouldn't it be really easy to just take that hydrogen off? Because wouldn't the oxygen be pulling the electrons, so wouldn't it knock the hydrogen off?
Yeah, you could lose just the H too. Yep, that could happen. I think.
No, don't listen to me. I'm just.
No, I think. Makes sense. You'd have H plus then, which is fine.
And that would be, wait, no.
Yeah. What about the? Okay, now what about the other one we need to do? So the alpha cleavage, and that is the homolytic version, right? So here, which bond do we want to break? So I previously made an alcohol that's symmetrical, right? So in an alpha cleavage, which bond are we breaking?
Alpha beta.
Alpha beta bond, right? So Alpha refers to, right, what's attached to the thing that has lost an electron. This is the 3 is the alpha carbon, right? It's also the name of my fantasy football team, the Alpha Carbons, and an awesome intramural football team name. I'm on the market for next year.
Yeah, we actually need a quarterback with the flags.
Let's break the bond between 2 and 3. So if we're going to break the bond, put the electrons between the bond, between the alpha and the beta bond, and we're going homolytic, so we're moving 1 electron at a time. So 1 electron's going between carbon 3 and oxygen. The electron that was on oxygen goes there, and then this electron goes to carbon 2. So you end up with a new pi bond, right? The lone pair is still on the oxygen, right? That one lone pair never changed, right? This lone pair here never went anywhere. 1 electron form that new pi bond. 4 and 5, right? So let's see. Number our carbons. 1, 2, 3, 4, 5. One thing people forget, I've seen a lot, people forget about this arrow. People forget, right, you can't move, if you're going to break a bond, you got to move both electrons, all this. Right, so make sure you show this other arrow going to carbon 2 here, the beta carbon. So where's that electron at then? That electron's at 2. And what else do I need? Plus charge on oxygen. And this is the piece we actually see, right? Good. You already know the mechanism for it. So let's say you have this. Step 1, of course, is NaNH2. Step 2 is this, right? So a strong base is going to deprotonate the alkyne, right?
There was something else though.
Yep, I'm going to put right here, there's a third step that maybe you guys haven't seen. NH4 Cl minus. And that was like step 3, right? So step 1 and 2 you've seen before, but step 3 you also know, really. So you end up here with an alkyne that's deprotonated, right? Negatively charged, good nucleophile. Then step 2 comes along. All right, we do backside attack, kick that out, get our final product. Plus, obviously there was Na plus along the way here. And there was, so there's Na plus, Br minus. And basically what the third step is for is just workup. Right, so this is a really weak acid. So you probably did this reaction, you probably had maybe had 1.2 equivalences of this to 1 of this. So that you'd have 10 moles of this and 12 moles of this. So you need to add the acid to basically quench or stop this stuff from reacting or doing anything else before you could like use your step funnel. So like you would add, right? You guys added like baking soda. Remember we did that reaction with a base. It must have been a base. What were we doing? The second step funnel thing we did. Eugenol, I think we used some sodium hydroxide and we had to like, right, use some baking soda. Right? So it's just basically a way you add this in to quench the reagents in your step funnel. That's what it's for. It's a weak acid that would quench this strong base. Right? Because this is so NH4 plus, right? That's an acid. And right? So any leftover NH2 minus will react with that really fast. So it just stops the reaction. That's all it is. You don't need to worry about that right now.
The answer, it was an alkene. It was a transalkene.
Then they were doing something else. It was a second step. It wasn't NH4Cl minus then. It was something else. So let's look at a reaction where we get a mixture of stereoisomers and how we'd recognize those. So let's say you have an alkene.
Do you have to buy our soda?
I do have to buy your soda.
Yes.
Really?
Yay.
Let's say you have that alkene and you have Br2, right? So, classic mechanism, pi bond attacks, goes there, back, and we know this makes a bromonium ion, that's right. And it could be from the top or the bottom, right? And it makes Br minus, right? So it can attack here, right? Oop. So we get a trans addition, right? Always get a trans addition. Good. Let's see. Oh no. So we've created a trans product, and this is not meso. This is right. This is not a meso compound. A meso isomer of this, though, would be, right, if we had both bromines going down, which would also look like, oh well. Right? Because a definition of a meso compound has asymmetric centers. That means it has something that's sp3 with 4 different things bound to it, but it doesn't rotate plane polarized light, right? It has a mirror plane. So if you look at this guy, there's a mirror plane down the middle, right? So the cis isomer of this is meso, right? Whereas the trans from the bromonium ion attack is not meso. It's an actual stereoisomer, right? So even though, so another good question, so if I have this and this, what are they to each other? Are they, they're diastereomers to each other, right? They have one stereocenter the same and at least one other one that's different, right? So these are diastereomers to each other.
So, and then how do you find the number of isomers again?
Usually the number of stereoisomers is 2 to the n.
I screwed up what I was saying.
Number of sevens.
Yep, the number of stereocenters usually have. Right, so in this compound, right, you have 2 stereocenters, right? But because one of those isomers, they're meso, you really only have 3 stereoisomers here. You don't actually have 4. You can't calculate it. If you have meso, right, meso compound is just 1 stereoisomer.
Just one.
Right, so it doesn't matter if these are hatched, right, that's one meso version, but if they're wedged, it's actually the same compound, right? It's not any different.